So we're going to talk a little bit about how lenses work. And we'll start with the idea that when light passes through an interface, so like between air and glass, the light rays are going to bend. And that is essentially what we're counting on when you're working with lenses and light. There's really two basic kinds of thin lenses. There's converging lenses and diverging lenses. And the reason we're calling them thin lenses is when you get bigger than that, it's a block of glass, the physics changes and the math changes. So we're talking about basically lenses you find in any optical tools like eyeglasses or telescopes or microscopes. They all fall under the category of thin lenses. And they have an optical axis, which is just right through the center of the lens, and that kind of guides all of the geometry for the light bending that tells us how the lens is going to work. So how lenses work is rays of light enter the lens and they bend when they enter and they bend again when they leave. And the shape of the lens determines how the rays bend. A converging lens bends the top rays down and the bottom rays up so that they meet at a point on the other side of the lens. And that point where all the light meets is called the focal point. And diverging lenses bend the rays outward so that they focus in front of the lens in a kind of an imaginary spot and not behind it. And this creates two types of images. One is a virtual image and one is a real image. And the virtual image is an upright image. It's either larger or smaller than the actual object. And you actually have to look through the lens to see it. So it's like how a magnifying glass would work. You can't really see the image of something that you're trying to magnify unless you see it through the lens. And a real image is inverted. It's either larger or smaller than the object. And the big difference between the inverted and the upright is that the real image can be projected. So this is how images end up on your retina. They're actually upside down. Movie cameras have inverted images. So they start off upside down so they can be upright when you look at them. And we have some different types of lenses. And I said, we've got converging and diverging. Convex lenses are generally converging lenses. They're thicker in the middle than on the ends. They form real or virtual images. Concave lenses are thicker on the ends and in the middle, and they only form virtual images. Convex lenses can both converge and diverge. They're used in eyeglasses, and concave lenses are used in telescopes and binoculars. And if you combine the two type lenses, you get what's called a compound lens, and where those come up most often is in compound microscopes. A little bit of vocabulary that goes along with lenses. You have the object distance, which is the distance from the center of the lens to the object. And you have the focal length, which is the distance from the center of the lens to the focal point, which is the place where all the light that passes through the lens will focus. And the image distance is the distance from the center of the lens to where the image appears to be. And if you want to know kind of how to find the image, if you're ever playing with lenses and you want to anticipate where the image is going to be, you can follow some basic lens tracing rules. And this is just for the converging lens. It's slightly different for a diverging lens, but it's not too much different. The first ray is going to be parallel to the optical axis, and then it's going to go through the lens and bend towards the focal point. You've got a second ray that goes from the top of that arrow straight through the center of the ray. And then you've got a third one that goes from the top of the arrow to the bottom of the lens. And then it carries on parallel to the optical axis. And where those three intersect is going to be the top of your image. If you start at the top of the object, you're going to end up at the top of your image. This is mathematical. As you can probably imagine, there's an equation for it. and it's called the thin lens equation. And 1 over the focal length is equal to 1 over the object distance plus 1 over the image distance. And if you're hesitant with math, be really careful with this one using your calculator or adding fractions. Remember, you need common denominators to add fractions. Or use your calculator carefully. Use the x to the minus 1 button. And then there's a second one that is just a ratio. The magnification of the image is going to be the image distance divided by the object distance. That tells you how much bigger or smaller your image is going to be. And this is kind of a drawing of labeling everything for your thin lens equation. Once again, the farther away the object is from the lens, the closer the lens is to the image. And I did an example so you can kind of see some numbers. If you have a candle placed 5 centimeters in front of a converging lens with a focal length of 2 centimeters, where will the image appear? And so you use that thin lens equation and start plugging things in. You can either rearrange or plug things in. So you have 1 over 2 centimeters is equal to 1 over 5 centimeters plus 1 over the image distance. And when you solve that out, 1 over the image distance ends up being 0.3, and it's centimeters to the minus 1, so I didn't put that on there. And don't forget to flip that answer so that you end up with the right number. It is 3.3 centimeters. And as long as your units are all the same, and this is all you're calculating with, you can leave it in whatever units you have. If you're mixing units for some reason, go ahead and change it to meters. Alrighty, bye-bye.